In this lecture, we'll discuss the introduction about state missions, or pattern detectors, or sequence detectors. We will discuss all four types of state missions like Mealy, Moore, overlap, non-overlap. We'll see a point wise. First, we'll see the definition. State mission is a circuit. It contains states, and those states change or transit from one state to another state. You know, when we observe a state diagram, it contains states, no? Okay, and those states change or transit from one to another. Okay, that is the definition. State mission can also in the form of state diagram or state table. Okay, the state mission can be in different forms. It can be in the form of state or diagram or graph, or a state table, or like a circuit also. Okay, logic diagram also. State missions are mainly two types: finite state missions and infinite state missions. The first two mainly types are two types: finite to infinite. Okay, of course we use finite state missions. Infinite state missions need infinite hardware or flip-flops, so it is impractical to design. That's why we don't use infinite state missions. Infinite means we need infinite hardware, no? That's not possible to design. Okay, that's why we don't use infinite state missions. But finite state missions are possible. We can design with finite hardware or finite flip-flops, right? Finite state missions contain finite states, finite flip-flops. So actually each state containing group of flip-flops. Whatever the states there, each state contain group of flip-flops. It based on the pattern, how many flip-flops. Okay. Again, these finite state missions are two types: implicit, explicit. We use explicit because of benefits over implicit, and real-time designs mostly suitable to explicit. Okay. But implicit is good up to two states, but real-time designs mostly contain more than two states, no? So that's why we use explicit. And one more thing, in explicit, states are clearly labeled. That's why the name came explicit. But in implicit, even though there are states existed, but they are not clearly labeled or visible. Okay, if the states are clearly labeled, we can understand the state transition clearly, no? Okay, that's the benefit of explicit. Some more benefits also there. Okay, suppose if we take a D flip-flop behavioral code in very log, it contains states reset applying and reset releasing, but we don't mention or we don't label them clearly, no? So it contains states, but they are not visible clearly. That is meant by implicit. Next, this explicit state missions again divided into two types: Mealy and Moore. Okay, we mostly use Moore. This Moore need one extra state than Mealy. Compared to same pattern, compared to Moore with Mealy, Moore need one extra state. It means it need more hardware. Even though Moore need more hardware, we use Moore only. Because the reason is in Moore, output detection or next state depends on present state and only present state. But in Mealy, output depends on present state and present data input also. Because of this reason, this is the main reason. Some more reasons can be there. We are using Moore even though it is complex. Okay. Again, this Mealy and Moore divided into two types like overlap, non-overlap. We mostly use Moore non-overlap in industries, and we encode the states using either straight binary or gray code or one hot encode. Okay, that encoding you can see in further slides. This gray code encoding suitable whenever there is a predictable nature of state transitions. Suppose if you take traffic light controller state mission, we can predict next what is the state. So in that kind of state missions only, that gray code encoding is suitable. Okay. Okay, if we want to calculate the number of bits or flip-flop in each state, flip-flops in each state with gray or straight binary encoding. This is the relation n less than or equal to 2 power n. Here n capital and whatever the n with 2 power, that is small n. So that capital N, if we assume as a number of state, and that small n will become the number of bits or number of flip-flops in each state. This is applicable only with the gray and straight binary. But when we take one hot encoding, number of states and number of flip-flops in each state both are same. Okay, right. In one hot encoding, any one bit of code word is 1. Remaining all other bits should be 0. Then only it will be a valid code word. Okay. One hot encoding is mostly used out of gray or binary, side binary, and one hot. We mostly use one hot encoding in state machines because it won't affect by temporary or invalid states. Because those invalid states become ignored because they contain more than one. That's the reason. It will become a invalid one hot encoding. No? That's why. So with gray, there is a less chance of invalid states. Okay, less chance of glitches, but they are suitable only when there is a predictable state transition nature. So we don't use straight binary encoding because of more possibility of invalid states or glitches or sequential hazards. Okay. So these invalid states nothing but they creating hazards or glitches, sequential hazards. Okay, in sequential circuits. So the solution to use this to avoid these glitches is in state machines is one hot encode. If you take Moore type state machine, either overlap or non-overlap, the number of states will be equal to number of bits of pattern plus 1, n plus 1. But in Mealy, number of bits of pattern and the number of states are same. It will be n. Okay. So finally, we'll see how to design a state machine or a circuit. Okay. So there are step-by-step process. We need to follow 5 steps. Okay. Here this 6 is mistake. Total 5 steps. One is state diagram. Then from the state diagram, we have to draw state table. Then from the state table, we have to draw excitation table of this design. So in this excitation table, we use some flip-flop. So we need to have that flip-flop excitation table also. Okay. Then after excitation table of design, we have to do K-map simplification for the output and flip-flop inputs. State machine output and flip-flop inputs. Okay. Then for all those simplified expressions, we have to draw logic diagram. Then that circuit will become the state machine circuit or state machine design. Okay. So introduction completed. So in other lectures, I explained the design clearly. Each step I did one lecture. Okay. And I will merge this introduction and those all lectures also as one lecture. Okay. Either you can see individually or one lecture at a time. And I sent the complete notes also as a PDF in your group, in WhatsApp group.